Yeah.
Okay, good afternoon, everyone. So let's start with today's class.
In the last class, we had covered the basic principles required for pre-processing, that means filtering the EEG signals. Today, we'll cover the feature extraction stages. Okay. So first, we are going to cover the feature extraction process in the frequency domain. So all of you must be familiar with what is Fourier transform. So this is the basic mathematical formulation of a Fourier transform. Now, before going into the details of the mathematical formulations, what we are going to study is the main physical interpretation of each of these transforms. Okay. So suppose I have a time domain signal, which is mainly an EEG signal. So what we get as an output of the EEG signal is amplitude versus time, right? And what we are trying to do is capture the frequencies hidden within this time domain signal. So that can be done by utilizing Fourier transform. And in Fourier transform, what happens is that this time domain signal is basically broken down into consequent sinusoidal waves to understand the different frequency changes of these signals. So what we get as an output is something like amplitude versus frequency. So previously we had amplitude versus time. Now we have amplitude versus frequency. So we are going to get these small frequency spikes indicating the different changes in frequencies taking place in the EEG signal. Now, there are certain characteristics associated with Fourier transform is that Fourier transform output is much more precise if I'm dealing with stationary signals. So what are stationary signals? So time domain signals which are said to be stationary, it means that it's certain characteristics like the frequency characteristics or its statistical characteristics like mean, variance. All these characteristics of the time domain signals, they do not change with time. Okay. So if it is kind of a static signal, I can easily apply Fourier transform to extract the frequency components. So this particular static signal or the stationary signal is getting converted into its frequency domain counterpart, and the signal representation can be utilized by this equation. So whenever the signal is stationary, if I'm applying Fourier transform, that is not an issue. But EEG signals are not stationary signals, right? Because when I'm capturing the EEG signal of a subject, I'm capturing it in real time. That means it is obvious that its characteristics, that is time domain based characteristics, statistical characteristics, it is continuously changing with respect to time. So that is why the EEG signals are referred to as non-stationary signals, because different types of frequency characteristics, statistical characteristics are continuously changing with time. Now, for such signals, suppose this is an example of a real-time non-stationary signal, which is the case for EEG signals. If I'm transforming it via Fourier transform, I will get these frequency spikes which I want to acquire. But unfortunately, since all its characteristics are always changing, I cannot trace back certain amount of information from these signals. See, the information is getting lost from here. So beyond these set of frequencies, the information is getting lost. Maybe I'm getting small frequency spikes in the beginning. And whatever frequency I'm obtaining via Fourier transform for non-stationary signals, that is also not very precise. because initially Fourier transform was developed for stationary signals. Hence, utilizing Fourier transform for EEG signals is not a good option. That is why we are going to move on to the more established version of Fourier-based analysis or frequency domain-based analysis. So the first version which we use instead of Fourier transform for non-stationary signal analysis is short-time Fourier transform. It is also referred to as Gabor transform. So Gabor is the name of the science. Now in this transform, what we are doing is, so Fourier transform, you had seen, it's basically the integration of the signal and this time domain signal integration. Now with this time domain signal ft, we are adding another term, that is omega t minus tau. Now what is this particular term? This omega term is nothing but it is explaining a mathematical window. So over here, what we are trying to do is that we have amplitude versus time, that is our original time domain based signal, the main EEG signal. Now we are putting a window to capture, and the window slides from left to right or right to left. Okay, so it can slide along the axis of the time domain to capture the abrupt changes taking place within the signal. Okay, so this is the basic philosophy of short-time Fourier transform. So once we apply this windowing mechanism to capture the abrupt changes in the frequency components, we get an output something like this. And this plot is not a 2D plot like we had obtained in Fourier transform, but rather it is a 3-dimensional plot. What we get over here, in one axis we have the amplitude, we have the frequency, and then we have the time. So within a single plot, we are obtaining 3 types of informations, that is amplitude, frequency, as well as time. So you can see how are the frequency components changing with respect to time. And of course, through the amplitude, we can understand the magnitude of these changes. So it is a much more powerful transform as compared to the Fourier transform. And of course, it is much more advantageous to utilize it for EEG signals because this is specifically designed for non-stationary signals, which is the case for EEG. However, short-time Fourier transform also suffers one main limitation. Now, what is that? The limitation is the concept of the time window. That means, first of all, how do I decide what is going to be the size or shape of the time window? Now, we know that frequency time and time are inversely proportional. That is how they are related. So what if I prepare a time window which has multiple time slots capturing different time domain based information, but if I'm doing that, I'm getting a poor frequency resolution because the frequency slots are reducing. On the second scenario, it is the opposite of the first scenario. If I am providing multiple frequency domain based slots to understand distinctly the different changes in frequency, the time slots are again reducing. So over here, I'm getting a good frequency resolution, but the time resolution is poor. So now this is the main problem. So I have to adjust my window size in such a way. So in this case, the window size is fixed for short-time Fourier transform. I cannot adjust it as per my need. So that is going to create this problem. Sometimes I'm getting good temporal resolution, sometimes I'm getting good frequency resolution. But what if I want both good time as well as frequency resolution under one platform? Then that becomes one of the most important drawbacks of short-time Fourier transform. And that is why we have a solution to this, that is wavelet transform. So before understanding the wavelet part, so this is a very basic diagram to illustrate what we have studied till now. So we have the main signal, time domain based signal, EEG signal, that is amplitude versus time. So over here, basically, I'm getting analogously, I have different time slots to capture the time domain based information. So once I'm transforming it into a frequency domain via Fourier transform, so what I'm getting is frequency versus amplitude. That means there are changes in the frequency slots, and with respect to that, I'm capturing the amplitude. Now, if I combine this original time domain based signal and the Fourier transformed frequency domain based signal, if I combine these two, then I get short time Fourier transform, which looks something like this. So you're just combining the vertical lines and the horizontal lines, and you're finally getting something in the form of grid lines. So under one platform, I'm getting the frequency versus time information. And of course, on the z-axis, I can just add the amplitude information. So I have not showed that for simplicity. But again, there is a problem with short time Fourier transform, which we discussed right now, is that all these time slots are of fixed size. But we have to vary the time slots in order to obtain good frequency as well as good temporal resolution. So that is done with the help of wavelet transform. So in wavelet transform, in certain places, we have different types of multiple time slots. So these type of shapes of the windows are going to capture distinctly the time domain based components, and these shapes are going to capture distinctly the frequency domain based components. So mathematically, what is actually happening? So I understand that I'm trying to utilize variable size windows in case of wavelet transform. But the question is, how do I design these variable size windows? So let's understand that. So first of all, we need to understand certain terms. The first term is, what is a wavelet, right? So wavelet means they are pulses or waves of short durations that helps me to provide different spectral as well as time domain based informations. That means what I'm talking about, the variable sized windows, these variable sized windows are nothing but a wavelet. These are the windows which are going to help me to provide good time resolution as well as good frequency resolution. So the wavelets, there are different types and shapes of wavelet which you can choose. I'll come to that later on. So first of all, say I'm choosing one particular shape of a wavelet. This is referred to as a Morlet wavelet. Now, whatever wavelet I am choosing, that is referred to as a mother wavelet. Okay. Now, once you choose the mother wavelet, you are either going to shrink or expand the wavelet as per your need to capture different time and frequency domain based information. So each shrinkage and compressed version of your mother wavelet are basically your child wavelets. Okay. So let me just show you with an example. Suppose this is the EEG signal which is acquired in real time. Now what I'm going to do is, you can see that there are various abrupt changes within the signal which I have to capture, right? And I'm going to do with the help of the mother wavelet, which is the Morlet wavelet in this case. Now I told you how to do this. The Morlet wavelet is nothing but your window. You are either going to shrink your window to capture these small abrupt changes, or you can expand this wavelet, that means you're expanding your window to capture these large abrupt changes. So this is the basic philosophy of how you're going to use wavelets as windows to capture different changes in your EEG signals. So the mathematically what you can write as the definition of a mother wavelet is provided over here. So that means the T part, this top portion, is your translation part, because you can move the wavelet from left to right or right to left, right? And this A part is basically scaling. That means scaling provides you either you can shrink the wavelet or you can expand the wavelet as per your needs. So if A is greater than 1, it refers to expansion. And if you vary the A value between 0 and 1, it refers to contraction. So you have a translational motion encountered by your mother wavelet, and you can also scale the wavelets, that is shrink them or expand them as per your needs. Now, of course, whenever you are choosing a mother wavelet, you have to maintain these two important characteristics. That is, the function must integrate to 0, because wavelets are basically short wave pulses which starts at whatever point it starts, it ends at the same point. So automatically the integration part is going to give you 0. And of course, the wavelet is going to have some finite energy. So that is why it is less than infinity. I hope the wavelet part is clear to everyone. Any doubts still here? Okay. So now let us see what are the different categories of mother wavelets which are available. So we took an example of the Morlet wavelet in the previous slide. We can have other wavelets like Dovecius, coiflets. They have different shapes. Biorthogonal, Mexican hat, singlets. Basically, these wavelets have been designed according to your practical needs. So the Dovecius wavelet is popularly used for capturing the abrupt changes in EEG signals. Then the Morlet wavelets are usually utilized in seismic waves, that is something to do with your earthquake, right? So for seismic technology, Morlet wavelets are utilized. Then you have these Mexican hat and coiflets. They are usually utilized in image processing tasks. So depending on different applications, these wavelets, mother wavelets, have been designed. So finally, what we get at the output is the same thing, that is your amplitude, time frequency. So basically, your time is basically referred to as your translation motion. And the scaling is basically done as a frequency component, that is, you are scaling the frequency components. So again, on the same platform, you're obtaining amplitude versus time versus frequency. So the plot might look something like this. And the best part is you are not utilizing fixed size windows. You can vary the window sizes so that whatever changes you are getting in your EEG signals, that can be captured with high amount of precision. So I have provided a compact chart through which you can easily understand what is the difference between Fourier transform, short time Fourier transform, and wavelet transform. So first of all, the first characteristics is the basis function. Anybody knows what is a basis function? Have you heard about this term? Okay, so basis function means what is the smallest component through which I can perform a particular transformation. So in case of Fourier transform, I'm breaking down the main signal into its sine and cosine components. Then I'm performing some kind of a mathematical operation. Okay. In short time Fourier transform, again, I am breaking down into its sine and cosine components, and I'm just utilizing a fixed size window with that, right? But in wavelet transform, my basis function, basic component is a mother wavelet. There is no concept of sine or cosine parts of the signal. Now, signal compatibility. Of course, as we have discussed, Fourier transform is more compatible with stationary signals. Short-time Fourier transform and wavelet transform, they can of course be applied to stationary signals, but they have been built for handling the characteristics of non-stationary signals, which is EEG signals in our case. Now, then we have the concept of window sizes. Of course, in Fourier transform, we do not have the concept of windows. In short-time Fourier transform, we are utilizing fixed-sized windows, which creates a major limitation. And that limitation is encountered by the wavelet transform, which has variable-sized windows. Now, what kind of resolution does this transform provide me? Of course, Fourier transform is going to provide me high frequency resolution, because what I'm obtaining as an output is frequency versus amplitude, or amplitude versus frequency. There is no question of time resolution. So it provides me a zero time resolution. In short time Fourier transform, we are getting both high time and frequency resolution, but both of them are very strict. They're very consistent. Okay. And over here in wavelet transform, we are getting high time and frequency resolution, but the resolution can vary because we are using variable sized windows. So coming to the application part, so what does Fourier transform actually capture from the signal? So Fourier transform provides me a global analysis. That means it basically captures the overall frequency components from a time domain based signal. I do not get any kind of information about those small abrupt changes taking place. Those information is not provided. So it gives me an overall computation rather than any kind of local computation. And hence we are saying that Fourier transform provides a global analysis. Now, short-time Fourier transform, on the other hand, we are able to see a local analysis because we can easily capture, the small abrupt changes, the rapid drifts which are taking place in the EEG signals. But however, the precision is very low because we are using fixed time windows. But in case of wavelet transform, of course, this is also a local analysis. We can easily capture the drifts and the abrupt changes, but the precision of capturing these changes is very high because of the use of the concept of wavelets, which can be either compressed or expanded or translated as per our needs. Okay, so this is the basic summary of what we have studied till now. Now, of course, a particular wavelet transform can be continuous wavelet transform. So that means you are just applying integration on the main time domain based signal along with the mother wavelet which you have chosen. It can be Morlet, it can be Dovetius, anything depending on the application. But whatever way you are applying the continuous wavelet transform, you are going to acquire certain coefficients, right, as the output. Now, certain amount of coefficients are quite redundant, which increases the computational complexity of this particular continuous wavelet transform. So to remove this redundancy and to make it more computationally inexpensive, we generally do not go for continuous wavelet transform. We go for discrete wavelet transform. So basically, this is the same equation. You can just discretize this. So you are just you are converting the integration into the summation operator, and over here you are using the mother wavelet as before. So over here I have just provided a short derivation. So this was initially your time domain based mother wavelet. You're just going to replace A with 2 to the power of k and tau with 2 to the power of k and l, where k and l are integers. And you know how to go from a continuous domain to discrete domain. You must have studied in your signal processing classes. So you're going to set t is equal to m of t. So that means you're just going to convert those continuous signals into certain discrete samples. And if you just put these values over here, solve it, you just get this output. So this is the discretized version of your mother wavelet. Okay. Now, in 1988, S. Mallet, he was a professor, he introduced another concept which is based on the discrete wavelet transform, which is referred to as the fast wavelet transform. So, fast wavelet transform is a more computationally fast version of the discrete wavelet transform. Okay, so you do not have to deal with any kind of redundancy, and the computational complexity is also very low. To make the computation much more faster and easier, Mallet introduced this concept. Now, while we are evaluating this fast wavelet transform, we generally deal with two types of coefficients. The first one is an approximate coefficients given as CA. Another one is the detailed coefficients, that is the CD. Now, what does approximate coefficient deal with? Approximate coefficient tells me the rough estimate of an overall information. And detailed coefficient, as the name suggests, gives me the finer details of any information. Now, let me give you a very analogical example for this, the concept, in order to illustrate the concept of approximate and detailed coefficients, is that suppose, imagine yourself, you're visiting a jungle, okay, and you have a passion for wildlife photography, say for instance. So you want to take the picture, so you are walking inside the jungle, and suddenly you see right in front of you a beautiful pine tree. Okay, it's a very rare species pine tree, and you've never seen this pine tree before, and you want to capture a picture of this pine tree with your camera. Okay, now suppose you're standing it statically in one particular position, and at a particular distance, the pine tree is right in front of you. So if you do not want to move from your position, what you do is first you capture the pine tree. That means you take a picture of the pine tree and you capture the entire pine tree in one particular frame. Now what you do is, now you want to capture the finer details of the pine tree, like what is the color of the bark, what is the shape of the leaves, what are the shape of the twigs, and so on and so forth. So instead of moving closer to the pine tree, what you do is you stand at the same position and you zoom in your camera, just change the zooming mechanism so that the finer details of the pine tree are captured. So you take 2-3 pictures of those finer details. One is for the leaf shape, one is for the texture of the bark, one is for the shape of the twigs, and so on. So with one particular camera, you are able to capture the approximate version of the main image. That means in one frame, you have captured the entire pine tree. So the average information about the pine tree is captured in that one frame. So this is the concept of approximate coefficients. It gives you a rough estimate of the overall information. And the other pictures which you have captured by changing the zooming angle of your camera, that is for the barks and the leaves and the structures of the tree, that is giving you the finer details. That means that is giving you the detailed coefficients. So in a particular signal, in a similar way, I can capture an average information of the signal. That is called the approximate coefficient. I can also capture the abrupt changes in details, like if there is a sharp drift or there is a large abrupt change. So all these finer changes can also be captured by this analysis, which is referred to as detailed coefficients. So whenever we are providing a time domain signal to this particular analysis, we are obtaining these two types of coefficient values. Now the question is how to arrange this type of coefficient values. How do we apply this process so that we get approximate coefficient as well as detailed coefficients? So over here, suppose you have the main EEG signal. You pass the signal to a low pass filter. And after that, you get an approximate estimate, which is your approximate coefficient, that is CA. You can pass the same signal through a high pass filter to get the detailed coefficients that is helping you to acquire the sharp spikes, abrupt oscillations, and so on. Now, this diagram, what I'm showing you right now, is the first level decomposition of the signal. You can continue decomposing the signal to multiple levels. So you can but the main thing is from which particular portion should you start decomposing if you're going for level number 2. See, this is the detailed coefficient. I cannot decompose my signal further from here. But since this particular thing is your approximate version, you can again pass this through a low pass filter and high pass filter, and then you will get an approximate version of this approximate version and the detailed version of this particular signal. Then you can continue decomposing it to level 2, 3, and 4 as per your requirement. Getting my point? So this is the main way in which you can decompose an EEG signal into different components to capture the frequency and time domain based informations via wavelets. Is it clear to everyone? Any doubts still here? Okay. So now I have to go back to my digital board. Just give me 2 minutes for that. Okay. So we have covered a large portion of our frequency domain based features, but one particular frequency domain based feature is left, that is the power spectral density. So our topic today is feature extraction techniques. Okay. So in the frequency domain only we are going to continue. So the last frequency domain based feature which we are going to discuss today is power spectral density, abbreviated as PSD. Now there are three terms over here: power, spectral, density, right? So density, all of you know what is the meaning of density. That means it says like per unit something. Like in physics you have studied that density means mass per unit volume, right? So it's per unit something, okay? From the word spectral, now you can understand spectral has something to do with frequency. So spectral means frequency domain. And power, you can understand the power of the signal. So that means power spectral density actually refers to power per unit frequency. That is what it tries to capture from the time domain based EEG signals. So first of all, what we have to do is, for applying PSD, is that you have to convert the time domain based signals into frequency domain. So from time domain, you're going to move to frequency domain. And you can perform that in any particular way. You can go for Fourier transform, short time Fourier transform, wavelet transform, and so on, right? We have seen all these things. So once you get the frequency components, what you do is you calculate the power of this frequency. So this is how you get the power of a frequency domain based signal, right? But for obtaining power spectral density, that means you have to get the power per unit frequency. What we do is we have this frequency domain based signals magnitude square divided by n into fs. So what is n? N is the number of samples and fs is the sampling frequency. Okay. So over here, I hope you can understand what is the meaning of samples and sampling frequency. So basically samples means they are the data points that make up this signal. So if you have this signal, they are the data points, the discrete values that make up the signal. Now, what is the link between number of samples and sampling frequency? Let me give you a short example. Say, as an example, for 20 seconds time, you are telling a subject to perform a mental calculation, during which, of course, you are taking the EEG signals from the scalp of the subject. Now, for every EEG device or any kind of brain acquisition device, there is a sampling frequency rated for that device, okay? The device we have in our AI lab, the sampling frequency is 500 Hertz. This can vary from device to device. So if I'm saying a device has a sampling frequency of 500 Hertz, what does it mean? It means that it provides 500 samples per second, right? So the total number of samples I am going to acquire for this 20 seconds time duration will be nothing but 20 into 500, that is 1000 samples. And these are the samples which are constituting my EEG signal. So this is the concept of sampling frequency and number of samples. Okay. So now we are over with the frequency domain based features. Now the question is, in the last class we had talked about different types of important BCI responses with respect to EEG signals, which were the spectral signals, then event related potentials, etc. Right? So under which type of signals will I utilize this frequency domain based analysis? That is the first question. So of course, frequency domain based analysis is applied to spectral signals. So in the last class, we had talked about two types of spectral signals. The first one was SSVP. What was SSVP? Can anybody answer? Nobody? So SSVP was the short steady state visually evoked potential. So what does it do? So if I am observing any kind of flickering of a particular object right in front of me, suppose it is flickering at 3 Hertz, my brain will capture that same frequency and start generating frequency of 3 Hertz. So that was steady state visually evoked potential, which we had discussed in the last class. Now for understanding whether the brain is generating the same frequency signal or not, as it is, as the human subject is seeing, For that, we have to apply, of course, Fourier transform, or we can go for short time Fourier transform or wavelet transform, because the main feature we need from SSVEP is to understand the frequency components, right? Now, there was another signal which we had discussed under spectral signals is ERD, ERS. So that was event related desynchronization followed by event related synchronization. So when do we see such kind of signals, especially during muscular movement or during the imagination of a muscular movement? That means during motor imagination. That means if I am physically moving or imagining to move my left arm, then the power of the signal first decreases and then the power of the EEG signal increases, right? So it is called event related desynchronization followed by event related synchronization. We had discussed this in the last class. So again, I'm saying what decreases? The power decreases, right? So over here, what we have to capture? Power versus frequency. So from over here for ERDRS, we are going to apply part spectral density, where the output will be power and frequency. So power changes versus frequency. That is going to be the output. Okay. Now we move on to the next category of EEG signal features, that is the time domain based features. We are over with frequency domain based. So time domain based features you can understand, like the original signal, EEG signal, is nothing but amplitude versus time. So within this signal, without going for any kind of change in domain, I can capture certain important information, which ultimately I'm going to feed that to a classifier or a clustering model to get some output, right? So there are different types of time domain based feature. The first one is the Zort parameter. So Zort parameter, what it does is it gives an approximate information about the frequency changes in the signal, but within the time domain. So I'm getting an approximate information about the frequency components, but without moving the time domain signal to frequency domain signal, like we have done before in Fourier or wavelet, right? So sitting in the time domain only, I'm getting an approximate information about the changes in the frequency components of the signal. Okay. So what is the main objective over here? It gives approximate information of the changes in frequency in time domain itself without Fourier transform or short time Fourier transform or wavelet transform. Okay. Now, how am I getting these approximate changes in frequency sitting in the time domain? Through certain statistical characteristics like changes in variance. So all those statistical characteristics helps me to get an approximate information about the frequency changes. So we have three types of Zort parameters. The first Zort parameter is activity. So activity basically represents the signal power, so which can be acquired via variance of a time function. Okay. So activity is defined like this. Okay, so yt is my signal. If you are calculating the variance of the signal, you're getting an approximate information about the signal power. So suppose whatever value you're obtaining as activity, so if the activity value is very high, it signifies large EEG amplitude change, and if the activity value is low, that means there is a small EEG amplitude provided. Okay, so activity is approximately providing me the signal power, not the exact value, because if I want the exact value, I have to again go for wavelet transform or short time Fourier transform. Okay, all right. The second Zort parameter is mobility. So mobility, it represents the mean frequency. Okay, so mean frequency component, or the proportion of standard deviation of the power spectrum. So mobility is defined like this, that is variance divided by variance of the original signal. Okay, so once I've applied mobility, if my value of mobility is high, it indicates faster signal changes, and if the value of the mobility is low, that means I can see slower signal changes. This is the main concept. The third Zort parameter is complexity. So this helps me to understand the change in frequency by looking at how much the signal deviates from a pure sine wave. That is the main objective. So what is the definition of complexity? Mobility by mobility of the mean signal. Okay. So if I'm getting complexity value closer to 1, that means whatever signal has been provided, signal is very simple signal, that means sine wave like. Okay. But if the complexity value is greater than 1, that means the signal is irregular or very complex, which is of course for EEG signals. Because for real time EEG signals, the complexity can never be close to 1. It is always greater than 1. Okay. So this is all about the mathematical part and what is the basic things Zort parameters covers. So let me shortly give you an overview again about the intuitive illustration of the Zort parameter. So I'll make a short table. We go to the next page only. So I'm giving you an intuitive illustration, like mathematically what I'm capturing through the three parameters. So parameter, what I'm trying to measure, and what is your EEG based signal interpretation. So the first parameter is activity. So I'm measuring the signal variance. And the interpretation is I'm actually trying to get an approximate version of the signal power. Second is mobility. Here I'm trying to capture the mean frequency. So as an interpretation, I'm trying to see the speed of changes within the EEG signal. And third is complexity. That is, I'm trying to see the shape irregularity of the signal. So basically, I'm trying to analyze the structure of the signal structure in comparison to a pure sine wave. So if it is the structure is very much similar to a pure sine wave, that is not possible for EEG signals, because of course EEG signals are real-time signals affected by artifacts. So of course it's not going to be exactly like a pure sine wave, but it's going to be more of a random signal, right? So these are the parameters of the Zort features, and these are the interpretations. So this table will help you to get intuitive interpretation of the mathematics we discussed a few minutes back. Okay. Now, so Zort parameters are over. We discussed the second type of time domain based signals, that is autoregressive parameters. So autoregressive parameter helps me to describe the temporal structure of the signal. Okay. Now there is a method of how it is done. So let me just give you brief points. It describes the temporal structure of the EEG signal. What do I mean by temporal structure is that how the signal evolves with time. With time, as time is progressing, how are the signal evolving, or what are the changes taking place in the signal, right? That is what is captured via autoregressive parameters. So the main idea behind it is that the current EEG sample can be represented or expressed as a linear combination of its previous samples plus a random error term. That means we are trying to predict the current EEG samples depending on these previous samples. And since I'm trying to predict something, there will be a small amount of error. So the current sample is that is y equal to previous samples plus an error term. Okay. So mathematically what we can write is that this signal xt as x a1 of t minus 1 a2 x of and this can continue till AP x of t minus p plus some error term. Okay. So of course you can understand what is xt, that is your current EEG signal sample, and A1, A2 till AP, these are your autoregressive coefficients or parameters, and P you can understand is the order of the model. That means how many past samples you are using, right? So number of past samples you're using to denote the current sample, and ET is your prediction error. Okay. So once we are able to represent this signal in this particular structure, what we do is, for classification or clustering, we save all these coefficient values A1, A2 till AP into a vector, and we just forward this to a classifier or a clustering model for making a final decision. So these autoregressive parameters or coefficients are the most important thing which we are going to extract and feed it to a classifier. Okay. Now the question is, I'm talking about predictions. So there are numerous number of ways in which this particular prediction can be done. Like you have the Yule-Walker equations, least square estimation, Borg algorithm. There are many more. Okay. So I'm not getting into those details. Only the basic part I'm covering is that how do you extract these parameters and what you're going to feed to the classifier. That is basically the coefficients A1, A2 and so on. Okay. So we are over with the time domain based features, and then we'll move on to another category of features. But till here, if you have any doubts, you can ask me right now. Okay, fine. So after time and frequency domain, there is another type of feature that can be extracted from EEG signals that is referred to as spatial features. Now, what spatial feature does is, suppose you have two data set, okay? Suppose you have data 1 and data 2, okay? Now, utilizing the concept of spatial features, they work on the concept of variance. So, it will show, like for the classifier, if data 1 belongs to class 1, that means its variance is very, very high compared to data number 2. So when both the data are provided to the classifier, it can understand, okay, the variance is high for data 1, that means it belongs to class 1. So this is the basic philosophy, what is being done over here. Okay. So what is the main goal over here is that you have to find spatial filters or parameters that maximize the variance of EEG signals of one class while minimizing the variance of another class which in turn helps in distinguishing between two different classes. Okay, so this is the main objective. So I am going to vary the variance and accordingly detect whether it belongs to class 1 or class 2. So I'll show you the basic concept of spatial features with an example. Okay, now a data set, first of all, suppose I have a data set like this. So you will have some values. Let me explain the structure of your data set. So a data set kind of looks like this. So the X1 components are the data from channel 1 and X2 components is the data from channel 2. So this is how an EEG data set looks like. Okay. Now let me show it with the help of a mathematical example. Suppose I have the first data set that belongs to class 1 and it looks something like this. I have another data set that belongs to class 2 and it looks something like this. 1, 2, 1, 2. Okay. Now, what is my objective? So there are various steps. Step number 1. I have to compute the covariance matrix for each of the data sets. So as we had covered in the last class, covariance matrix kind of helps to understand the correlation component, right? So how are the channels correlated among themselves? So that is what covariance matrix provides us. We had done an example in the last class, if you remember. So let's calculate the covariance matrix C1. The formula is X1, X1 transpose. So this was the main matrix. You take the transpose of this. So if you multiply these two, you get an output. This is your final covariance matrix for X1. Now what you have to do is you have to normalize C1. So there are different ways of normalizing C1. Under normalization, first you have to calculate the trace. So what is the trace of this matrix? 10, 9, 9, 10? Yes. What is the trace of this matrix? You have studied what is trace, right? $20, right. So basically 10 plus 10, you just add the diagonal elements. So that is 20. So for normalization, what we do is we divide each component by 20. So we get the output something like this. So this is the normalized matrix. So this is for x1. Similarly, I have to calculate covariance for x2. So you get the output. Again, you have to normalize C2. The trace is again 20 over here, 10 plus 10. So finally, you get normalized versions of the covariance matrix for x1 and x2. That is over. Now, what is step 2? For step 2, you have to evaluate the composite covariance. So that means simply add the two covariants obtained, C1 and C2. So adding them, you will get this as the output, and this is nothing but what kind of matrix is this? Yes, what kind of a matrix is this? The name of the matrix starts with I. Right, it's an identity matrix. Okay. Now we move on to step 3. You have to solve a generalized eigenvalue problem. So what is that? It is defined as C1W is equal to lambda of this composite thing. Now since we already know C equal to I, which we found out, so C1W is equal to lambda W. So W is basically your spatial filters which you have ultimately have to compute, right? That will help me to identify which data set has more variance. Okay. So now we move on to step 4. So for this you have to compute. Rather, I would say this is a part of step 3 only. Okay. So maybe I'm just writing A and B. So now you have to compute the eigenvalues and eigenvectors. So for C1, we had this particular matrix. You know how to calculate eigenvalues. And equate this to 0. Right. And once you solve this, you will get the values of lambda These are the values of lambda. So these are your eigenvalues. So corresponding to each eigenvalue, you have to calculate the eigenvector. So for lambda 1 equal to 0.95, so basically you have to calculate so put in this equation, you will get the first vector. You know how to calculate it, I'm not showing it. This, and for your eigenvalue 0.05, the vector, if you calculate in a similar way, you obtain is 1 minus 1. Okay. So these two vectors which we obtained, the eigenvectors, these are your spatial filters. Okay. So now the final step, that is step 4, you have to project the EEG signals along your spatial filters. So the projection mechanism is Z is equal to W transform X. X, you can keep two components, X1 and X2. Okay. So for W, you have these two vectors, right? So I'm taking the transpose. You get something like this. So for Z, and you have these two X1, X2 components. So if you solve this, so Z will also have two components. That means Z can also be written as Z1, Z2, right? So, or if I am solving this equation, Z1 is equal to X1 plus X2 and Z2 is equal to X1 minus X2. Okay. Now we have to check using these two equations, like X1 data set, it has more variance for class 1. That means it belongs to class 1. I have to check all those things, right? So how would I do that? So let us make certain calculations. For class 1, I am checking. So I have my covariance matrix, that means X1 if it belongs to class 1. Okay. And over here in the covariance matrix, the diagonal element is actually depicting the variance, which in this case is 0.5, and the off diagonal component actually depicts the covariance of the individual terms x1 and x2, which is same in this case, that is 0.45. Okay. Now first equation was what? So equation number 1, equation number 2, x1 plus x2, right? So in the first scenario, z1 is equal to x1 plus x2. Let me check where the variance is more, for class 1 or class 2. So how to do that? So I have to find out the variance of x1 plus x2. You must have studied this in statistics. This can be written as variance of x1 plus variance of x2 plus 2 into covariance of x1 comma x2. So we know the variance of x1 from this matrix. So they are same, 0.5, 0.5 plus 2 into the correlation between the two components, that is 0.45. Okay. So we get the answer as 1.9. Now, if I have to find out the same thing for class number 2, so class 2, I had the covariance is something like this. So again, I'm going to utilize the same formulation, variance of x1, variance of x2 plus 2 into covariance of x1 comma x2. So over here also we can understand the variances are same, but the covariance is different. And this answer is 0.1. That means this equation z1 is equal to x1 plus x2. What is this indicating? High variance for class 1 and low variance for class 2, right? That means using this equation, I can understand that data of set 1 belongs to class 1 because it indicates a high variance for class 1. Similarly, you can go for the second equation, that is z2 is equal to x1 minus x2, through which you can obtain that there is a higher variance for class 2, through which you can conclude that data set 2 belongs to class 2. Okay. So this is how we are going to calculate spatial filters. The method which we utilized over here of spatial filters, it is referred to as a common spatial pattern. That is CSP. This is a basic CSP algorithm. There are variants of CSP algorithms, but we covered the common spatial pattern algorithm, the very basic one. Okay. Now, in the last class, we had talked about the important BCI responses, and we covered that the spectral signals, that is SSVP and ERDRS, for that the features I need to extract, one is power spectral density, another one I can go for short time Fourier transform, Fourier or wavelet, right? But we had also another type of BCI responses, that is event related potentials, ERPs, under which we had P300, N400 and so on, right? So these are time domain based potentials or time domain based signals. So for that we are going to utilize time domain based features like the Zot parameters and the autoregressive parameters. Okay. Now the question is, before extracting these Zot parameters or autoregressive parameters, what we have to do is, first of all, we need an extra step. What is that? Suppose in a single session, okay, so you remember what the ERP was, P300 signal. What was P300 signal? In the last class we had discussed. Can anybody elaborate? What was P300 signal? Okay, so for people who were not present in the last class, I'll just give you a brief description. Is that during an oddball stimulus, that means suppose I'm concentrating towards a particular work and suddenly I hear a bombastic sound outside. That means my concentration is going to get deviated, right? So at the point where I'm hearing the bombastic sound, so after 300 milliseconds of the sound, I'm going to get a positively rising signal inside my cortical region of the brain. So this signal, that means after 300 milliseconds, and I'm getting a positive peak, this is referred to as P300 signal. So it's a time domain based signal, amplitude versus time. Okay. So for such type of signals, we have different types like N400, P1000 and so on. Okay. For such type of signals, I need an extra step before extracting the time domain based features. What is that? Suppose in a session, for every trial, I'm going to get a P300 signal. So this is the first P300 signal, trial 1, trial 2, another P300 signal. So maybe there is another trial, trial N, this is another P300 signal. Okay, I'm erasing this part. So I might have large number of sessions in a particular experiment, say n number of sessions, and each session can have multiple number of trials. So what will I do is, for ERP detection, I'm going to take the average of all the data points, individual data points, okay, for this session. So I'll get an average signal like this, okay. Again, for the init session, the same thing. I will perform the average. So this continues. I'm going to get an average signal from all the trials, okay. Now what we are going to do, we are going to find out the grand average value of the signals. That means whatever average values you have obtained, that means average number 1, average number 2, from average number n denotes the total number of sessions. So all these signals you are going to average further to get the final ERP signal. So this is the grand average signal. Okay. So this is your final P300 signal. Upon this final P300 signal, now you can apply Zot parameters or autoregressive parameters or spatial filters to extract the most important features, that is the information, and feed it to a classifier or a clustering model. Is this part clear, what we are trying to do in case of ERPs? Okay, very good. So this is all about today's class. If you have any doubts, you can ask me right now. Okay, so the next class is on 21st. So 21st is a national holiday. So we are not going to have a class on that day. So after that, we are going to have a class. That means on 28. That means next to next Saturday, we're going to have the next class. Okay. Okay, fine. So thank you, everyone. I'm ending the session.